Hello, okay, you're welcome to the next video. So we start with number 11. In the nuclear reaction, what is the particle X? Now here we need to balance this nuclear reaction, of course, and we can see that for a nuclear reaction to be balanced, the mass number of this left hand side must be equal to the total mass number of the right hand side. The atomic number of the left hand side must be equal to the total atomic number of the right hand side. So this is 238, this is 234, that means this has to be 4 to make it balance. This is 92, this is 90, so 90 plus 2, that makes it 92. So the only particle that has a mass number of 4 and atomic number of 2 is the alpha particle. So B is the answer to this question. Okay, so the next one says complete the nuclear reaction, and what is the particle X? So the nuclear reaction here, if you add this is 14 plus 4, 18. This is 17, that means this should be 1 to make it 18. This is 7 plus 2, 9. 7 plus 2 is 9, so this is 8 plus 1 to be 9. So the only particle that has 1 is proton. Proton has a mass number of 1, atomic number of 1, so the answer is C. Good. So that leads us to number 13. In beta decay, the reaction the particle is, of course, I don't need to be told, since it is called a beta decay, it is definitely a beta particle. But we can go ahead and check. This is 14, this is 14, that means here has to be 0 to make it 14. This is 6, this is 7, here has to be minus 1 to make it 6. And beta particle has mass number of 0 and atomic number of minus 1. Amazing, amazing. Okay, so that leads us to the next one. Now, the binding energy per nucleon is greatest for nuclei with mass numbers around. Now, the peak of binding energy is iron with a mass number of 56. The lowest is hydrogen. So it goes from hydrogen, it peaks at 56, then starts coming down, So the peak is at iron, the mass number iron. Okay, that's by the way. You may not need that information for your exam, but no knowledge is a waste. The next one here says the mass defect of a helium-4 nucleus is 0.0304 U. Okay, that's U represent atomic mass unit. That's the unit we use to measure particles, because of their size being too small. So using E equal to delta mc squared, and where one atomic mass unit is 931.5 mega electron volts per c squared, the binding energy of helium is approximately, now the formula for binding energy is equal to the mass defect delta m then c squared. Okay, now but since we are if we are given the mass in kilogram and we are given the speed, we can use this formula. But here we are not given the mass. Actually, you can find the binding energy directly from the atomic mass unit. And so the binding energy in this case, now since we are given atomic mass unit, and one atomic mass unit is 931.5 mega electron volts, okay, that would mean that 0.0304 atomic mass unit is going to be 0.0304 multiplied by 931.5. Okay, so that is going to give us 28.3 mega electron volts. 28.3 mega electron volts. So the answer to this question is C. Very interesting. Okay, so the next one here has to do with binding energy and nuclear reactions. So it says in a nuclear fission, energy is released because, remember, nuclear fission is when two light nuclei come together. They combine together or they react together to form a heavier nuclei. So option A says the product have greater mass than the reactant. The binding energy per nucleon of the product is greater than that of the reactant, and a heavy nucleus absorbs a nucleon and becomes stable. The products have lower binding energy per nucleon. Now, if energy is released, for energy to be released, it simply means that of the reactant is greater than that of the product. That's what it means for energy to be released. Okay, so the answer to this question is D, because the products have lower binding energy to be released. Now, let's say you have something like this. I want to give you an example. 31T giving us let's say He42 plus this is 0 1. Okay, let's say you have this plus energy. Now, for the energy to be in the product side, it simply means that the reactant side, the energy of the reactant is greater than that of the product. This is just an example of binding energy. Two light nuclei, very light. You can see that one has a mass of 2, the other has a mass number of 3. So they are light. They combine together and release a great deal of energy. Kindly note that. Okay, so number 17 says nuclear fusion releases energy because the answer to that question, A, says light nuclei split into smaller fragments. That's not true. B, light nuclei combine to form a heavier nucleus with greater binding energy per nucleon. That's not true. C says the product nucleus has more protons than the reactants combined. That's also not true. Then D says the gamma rays are absorbed by the reactant nuclei. Okay, that's not true. The only one that looks this is fusion. Fusion simply means light nuclei combine to form a heavier nucleus. Okay, this is correct. So I think the other one is a mistake. Fission is when you split a heavy nucleus. Okay, so the answer to this question, well, this is still the answer. The answer we chose is still the answer, because for energy to be released, it means that reactant is greater than product. So the answer is still correct. But fission, Fission, has to do with splitting. Okay, while fusion has to do with fusing. Okay, so the next one, number 18, this one has to do with mass defect calculation. The mass of lithium 7, and that's the nucleus, is 7.0160 atomic mass unit. Given that the mass of proton is this and neutron is this, what is the mass defect? Very, very simple. Now, lithium has a mass number of 7 based on what we can see here, and atomic number of 3. Okay, so what that simply means is that lithium has, if you subtract, you get 4. That means lithium has 3 protons and 4 neutrons. So this is actually a mistake. This shouldn't be written here. It should be written here. Okay, so if you subtract 3 protons, mass number minus atomic number gives us the number of neutrons. That's why we say 4 neutrons. So if we check this now, you're going to have, since a proton weighs this is going to be 3 times 1.00728. Then plus for neutrons, it's going to be 4 times 1.00867. Okay, so this one is going to give us 3.02184. That's what this is. Then plus this is going to be 4.0, and this is going to be 3. Okay, let's see. This is 3, this 32 plus 2, that is going to give me 34. Okay, this is 24. Okay, so this is going to be 8 plus 2 is 6, and here is 28. Okay, good. So this is what we have. I don't have a calculator here, so if this adds this 3.02184 plus 4.03468, this is going to be this is 12, 14, 15, 5, 6, this is 507, 7.05652. So by the time you add up the masses of the protons and the neutrons, we are going to get 7.05652. Now this is where binding energy is about comes in. So the mass defect is going to be the total mass of the protons and neutrons minus the mass. This is how energy is produced. This is what binding energy is all about. The difference in mass, of the protons and neutrons and the molecule itself, the atom element itself. So here now we got 7.05652 minus this is 7.0160. so this is going to be 2, and this is, I hope I am getting this is 5, this is 0, this is 4, this is 0, this is 0. I hope I didn't make mistake somewhere. Okay, so 0.4052. I know I made a mistake somewhere, but this seemed to be the closest to my answer. Yeah. Now that leads us to the next one, number 19. A nucleus has a marked defect of 0.1 U, and since we have 1 atomic mass unit, this is the equivalent energy of 1 atomic mass unit, and that means its binding energy is going to be, if 1 atomic mass unit is 931.5, that means 0.1 atomic mass unit will be 0.1 times 931.5 mega electron volts, and that's going to be 93.15 mega electron volts. Very important for us to note. So the answer here is B. Okay, I wanted to avoid this one. So here in the fission reaction, this is a fission, splitting of this into this. It says the mass difference is 0.182. that's the mass difference, and the energy released is this. Well, it's still the same thing here. That means the binding energy here is going to be 0.186 multiplied by 931.5 mega electron volts. Okay, and that is going to give us 173.3. I have my way of estimating, don't ask me how, but I want to end up with this, that in cases where you are given the mass, let's say mass is 9.1 times 10 to the power minus 31, and you are given the speed of light like 3 times 10 to the power 8, and you're asked to find the binding energy. The binding energy would be the change in mass, which is this, then square of this. Okay, so it's going to be 9.1 times 10 to the power minus 31 multiplied by 3 times 10 to the power 8 squared, which is 9 times 1.1 times 10 to the power minus 31 times 9 times 10 to the power 16. You can do your calculation, and I think this is 81.9 times 10 to the power minus 15 joules. Okay, so the energy can be represented in joules and can also be represented in mega electron volts. Thank you very much. See you in my next video.